Everyone, welcome back. Yeah, I'm in the corner this time. So here's a more large problem, which might be harder for you because there's just so much information that's given, and not all of it is needed. So let's see if we can figure this out. So humans require about 85 moles of oxygen per day for survival. It is desired to have an emergency backup oxygen supply stored in a pressurized container. The container must be sufficient to supply the oxygen needs of 6 people for 2 weeks. Okay, so far so good. Assume the temperature of the oxygen in the tank is maintained at 10 degrees Fahrenheit, and the tank is designed to withstand a pressure of 150 pound-force per square inch. And the formulated oxygen as O2 is 32 grams per mole. What is the volume of this container in gallons? Woo! Woo! You might be freaking out a little bit here. You're like, oh, what is with this problem? That's okay. We'll get through it together. Or we won't. Okay. First off, PV equals nRT. Okay, pressure is given to us, so we're good there. Volume is what we're trying to solve for. Temperature is given to us. We're not quite good there because you can't use 10 degrees Fahrenheit. You have to use something different. You'll need to use Rankine or Kelvin. Let's go to Kelvin because that'll make it easier. And ideal gas constant is not really given to us, but we're going to use 0.08206 atmospheres liters per mole Kelvin. Okay, so we're going to do that, and we'll keep on going from there. Now, let's see if we can solve everything else. So what else do we have to do? Well, 85 moles of oxygen per day. We need to figure out what the number of moles is. So 85 per day, okay. And we want a backup support supply for 6 people, so times 6. And for 2 weeks, so times 14, because 14 days, 2 weeks. That's a lot. That's a whole lot of oxygen right there. Okay. But you gotta do what you gotta do. So, with that we have our number of moles, we have our temperature sort of. So let's convert temperature next. So 10 degrees Fahrenheit. I'm going to show you the way I would do it. So I would first convert to Rankine by adding 460. So this would be 470 Rankine. And then I convert to Kelvin by dividing by 1.8. So I divide by 1.8. And what do I get? I hate to mental math. Let's bring in my calculator. So 470 divided by 1.8. 261 Kelvin. Okay. So I have everything. I know temperature, I know pressure, I know number of moles, I have my ideal gas constant. I can solve for everything in liters, not in gallons yet. So I'll plug it in there. So I want to get my volume. So I'll put my number of moles first. 85 times 6 times 14. That's a lot of moles. Times the ideal gas constant, so 0.08206, times the temperature, times 261, and we have one more issue in the fact that that's PSI, and our little thing right here needs atmospheres. Well, there are 14.7 PSI per atmosphere, so 150 pounds per square inch, 14.7 on the bottom, and that's 1 atmosphere. That's going to be right around 10. Not quite, but close to it. I'm rounding a little bit here to save us some time. And let me get my other one up. So I'm just going to divide this by 10. 15,292 liters. Not gallons here, liters. Now a liter is about a fourth of a gallon. It's not exact. So just to save time, I divide this by 40. It's a good ballpark number. So somewhere around 3,823. But that's not an exact number because I didn't convert it exactly. So you're going to need to look up what the conversion is from liters to gallons. I'm going to let you do that on your own. But in the end, if you do it correctly, you'll get 3,955 gallons. Because here's my little thing right there. A liter is a little bit more than a quart. Okay, so all the steps are here. I mean, everything is here that you need. And the last thing I want to talk to you about is this. Look at this problem statement. This information that was given right here, the molecular weight of O2, was completely to throw you off. That happens in problems. If you're like, why do you do that? Why are you trying to confuse us? I'm not really. I'm trying to get you used to real life because you're going to be working with people and people have no idea what they need to tell you. Just think of the grandma who's trying to help you fix her computer. If her computer's broken, she thinks it has a virus, and she starts telling you everything that's happened in the past week with her computer. It died the other day. Did you have the cord plugged in? Oh no, it wasn't plugged in. It wasn't charging. I got an email. Oh, did you download something? No, it was from your mom. Oh, okay. Cool. Good talk. And just all this information that isn't actually helpful, but maybe in there she might say something like, oh, I was, watching a video and they got this weird link and told me my Flash player was old and I needed to download a new one. You're like, oh, well, there you go. That's your issue. So you got to learn how to discern what is useful and what is not. So with that, I hope this problem helps you. And there's a whole lot of writing here, but there's a much more concise solution on the next page. And I'll go ahead and show that at the end just so that you can be looking at that for next time. Okay, hope this helped you. See y'all next time. Bye-bye.